Let's get started. These questions ought to look familiar. I think they're in the neighborhood of 60 of them. And so we shouldn't have to spend a whole lot of time on each one. Let's see. So number one is just identify which one of these examples is a quantitative observation. Remember the difference between quantitative and qualitative. Qualitative expresses a is a descriptive term, such as color, relative size of one to another, any differences between the two that had no values attached to them. If you have a number, or ideally a number and a unit of measure, then you're talking quantitative. So if we look down the list, we find that D, the temperature of the liquid at 60 degrees, the temperature of the liquid is 60 degrees. That is a quantitative observation. Right. Number two, which of the following has a different value on the moon compared to the Earth? The first one, mass, is the same everywhere in the universe, except in relativistic situations like near a black hole, or when you're traveling close to the speed of light, then mass has a different meaning. But for our purposes, mass is the same everywhere. Weight, however, is different. Weight depends upon the gravitational attraction between two bodies. So if I'm standing on a smaller body, my weight will be less, such as on the moon. In fact, on the moon, my weight will be 1/6 what it is on the surface of the Earth. Time is the same everywhere. Moles is simply counting how many of something there is. So mass, time, and moles are the same on Earth and the moon. Weight is different. All right, 3. All the following characteristics of nonmetals, all of the following are characteristics of nonmetals except. So let's see. Poor conductors of heat. Yeah, that's true. Nonmetals are poor conductors of heat in most cases. Right? There are some exceptions. For instance, carbon nanotubes. You know what carbon nanotubes are? They're carbons that are linked together in hexagonal shapes. They're kind of like graphite in a cylinder. They are good conductors of electricity, but for most nonmetals, they are poor conductors of heat. They are brittle. They are brittle if they are solids. Okay. Ductility. Ductility is a characteristic of metals. Ductile means it can be stretched into a thin wire. Dull appearance is characteristic of nonmetals if they're liquids or solids. So the one that best fits, and E, they tend to gain electrons in chemical reactions. That's true for nonmetals. For instance, halogens. All the halogens tend to be a -1 charge if they're combined with a metal. So C, ductility. Well, let's see. Except. So this is the exception. These do not fit the exceptions. So C is the exception. That ductility is characteristic of metal, not a non-metal. All right, a little nomenclature here. All right, what's the correct name for this compound? Right? Is it a type 1, type 2, or type 3? It's definitely not a type 3 because there's a metal and a non-metal. So it's either a 1 or a 2. Now we have to decide the tiebreaker for 1 or 2 is, does the metal Can the metal have more than one charge in compounds? And in this case, it is. It's a transition metal, one of the transition metals that does have the possibility for multiple charges. So we say iron, oxide, and then we state the charge on the iron. Well, oxygen is a chalcogen. It's always -2. Right? So -2, this one has to be a +2. That means that's a Roman numeral 2. Iron 2 oxide is the correct name, which would be D. The correct name for Ca2 plus. All right. The key to this one is, first of all, that's calcium. All right. Where does it exist in the table? Calcium is in the second column, which would be alkaline earths. Alkaline earths are a fixed charge. That is, they're always 2+. So this 2+, remember when we're naming things, we have to meet two conditions. First condition is that the name has to be unambiguous. In other words, it can't be anything else but that. And it has to be non-redundant. So we don't have to say that this is a 2+ charge, right? We don't have to say that because all alkaline earths are 2+. So it's just calcium ion, right? It's unambiguous and not redundant. Calcium ion. So that would be B. Okay. About 6. I guess I better scroll if I'm going to get 6, huh? All right, everybody remembers these figures. And what we're trying to do is represent individual elements as simple circles, squares, grayed in or clear. Those represent elements or atoms. And if you have a different element, it's going to have a different shape or a different color. So, for instance, this B is going to be a solid because it's all the same element, right? It's all the same element and they're regularly spaced, which is typical of solids. The C is going to be a compound, right? This is a molecular compound of 2 elements, right? And there's only that compound in this figure. A has different atoms, but they're spaced wide apart. They're not all the same. So it is a mixture. And they're widely spaced, so it's a gas. And it looks like the shapes and the shadings are different. So it's a mixture of several gases, not just 2, more than 1. Then D is probably a liquid mixture of 2 elements. Right? You have all circles, but some are cleared, some are gray. So that's either an amorphous solid or a liquid. Probably a liquid. And for E, you have both elements and compounds mixed together in regular arrangement. This is a uniform or homogeneous mixture. So let's look at 6, which best represents a heterogeneous mixture of 2 elements. Heterogeneous means it's not uniform throughout, right? So, and a mixture means that, and based upon the question, there have to be only 2 elements, right? So can't be C, right? Because those are compounds, only compounds. E is compounded elements, so it doesn't work either. A is homogeneous because it's a gas. All gas mixtures are homogeneous, so it's not heterogeneous. The only one left is D. D has 2 elements in it, and they're not uniformly mixed. That's heterogeneous. So D would be the correct answer for 6. All right. Oh, and 7, which best represents a homogeneous mixture of an element and a compound? All right, an element and a compound. The only one that fits that actually is E. You got a compound here, and you got elements here. Right, those are the only two you have: the one compound type, the one element type, and they're regularly spaced. So we call that homogeneous mixture of an element and compound. That would be E. So 7, go ahead and put that one up here. 7 is E. Now, I wouldn't let what I've been saying just go in one ear and out the other, because suppose I offer this set of figures and I ask a question that's not one of these that I'm going over here now. Well, I've explained what each one is, so you need to remember that. Then if you get a question that's not part of these that are on the review document, then you'll be able to answer it. Let's see, we're also going to do 8. So what is 8 looking for? A solid element. Okay, there's your solid element right there. Right? Regularly spaced, only one type of atom. And that fits as B. All right. That statement is also true when we get to the point where we're going to work some problems. Right? If you just memorize the answer to those problems, chances are you're going to get it wrong in the exam. As if it looks like you've seen it before and you get the answer that you think is right, you better be able to work the problem. Because I may be just sneaky enough to change some of the parameters and come out with a different answer. All right. Let's see. 9. All the following are in aqueous solution. That's important. Notice what we have here. We have compounds with an H in front of it. Right? If you put that in aqueous solution, we're going to name it as an acid. So you need to know the acid naming convention in this case. So for, let's see, do I need to put all those up there? Which is incorrectly named. All right. All right, is H2SO4 sulfuric acid? Well, remember what the rules are. If there's oxygen, if you have oxygen in the name, then you do not start with hydro. In fact, what you do is you go to the non-hydrogen part of the name and say, what is that? And it's going to be a polyatomic ion. What is that polyatomic ion? Sulfate. All right. And H become X. So this is sulfuric acid. That one's correct. H2CO3. Right? No hydro in this one either. This is carbonate. So 8 becomes X. It's carbonic acid. That one's correct. Next one. No hydro in this one either. Oxygens. So this is phosphate. 8 becomes ic. This is phosphoric acid. Is that one correct? Yes. HCl. No oxygen in this one. So we start with hydro. We take that chloride and I becomes ic. We say hydrofluoric acid. Okay, that one's correct. Process of elimination, This one's probably not correct. There's no oxygen in there. What is this? This is cyanide. Polyatomic ion. I becomes ick. But we start it with hydro because there's no oxygen. So we say hydro cyanic acid. That's the wrong one. Right? So there's your answer. Okay. Let's see. Consider these three targets. All right. Number 10. What we're looking for here is to identify both accuracy and precision. Well, the question, of course, it looks like the question only is interested in precision, but we're going to talk about all three of them, right? How about number 1? Is 1 accurate? In order to determine accuracy for multiple hits, you say, where's the average position? The average position for those 5 hits is not on the bullseye. So the first one is not accurate. Is it precise? Precision is grouping. That's a poor grouping. Those hits are very far apart. So it's not precise either. Okay. How about the second one? Well, looks like it's fairly precise, right? This one is precise. But is it close to the bullseye? No, it's not. No, so it's not accurate either. And 3. About that one. That one is on the bullseye. And it's a tight grouping. All right. So to answer the question, which of the following figures represents results having low precision? Low precision is only this one. Right? Only that one. That's A. Let's see, we're missing one, aren't we? Yeah. We're missing one that's not precise, but accurate. So the grouping would have to be such that the average of the hits would be on the bullseye. That would be an accurate group of measurements, but not precise. All right. Let's see, 11. Yes, 11. The amount of uncertainty in a measured quantity is determined by what? If you're going to be working in a lab, you want to know 2 things. How's your instrumentation? Are your instruments calibrated properly? Have they been standardized? If you're part of if you're working in a lab that is, it requires certification periodically, then you want your equipment to be well maintained so that when the inspectors come to check it, they're going to find that your equipment is in good working order, right? Second thing they're going to check for is how good are your determinations, right? So you can have good equipment and lousy results. If your technicians don't know how to operate the equipment, or they're sloppy, or for a number of other reasons that you can pin on the operator, right? So both the skill of the observer or the operator and the limitations of the equipment are the 2 factors that will determine whether your measurements are good or bad, right? Uncertainty is in a measured quantity is determined by those 2 factors, the observer and the instrumentation. So 11 would be C. Which of the following are incorrectly paired? Okay, so this one, you have to know, where are these things located in the periodic table? Right? Is there a name for that group? Yeah, alkaline earth metals. That one's true. V, vanadium, where is it located? It's a transition metal. Cl, where is it located? It's a halogen, along with fluorine, bromine, and iodine, and astatine too. H, is hydrogen a noble gas? I don't think so. Its next door neighbor is helium, but hydrogen is not a noble gas. In fact, hydrogen is positioned above the alkali metals, but it's not even an alkali metal. It's all by itself. Hydrogen is an animal unto itself. And of course, uranium is an actinide metal. Right? So hydrogen is the one that's misidentified. The boiling of water is what? First of all, is it a physical or a chemical change? Right? It's a physical change. Now, why can we be sure that it's a physical change? Is it because the water merely disappears? Well, I can make water disappear with a chemical change too. Right? I can run a direct current through it, and one electrode you get hydrogen, the other electrode you get oxygen. That's a chemical change, and the water disappeared. So that's not a good explanation. If it's a physical change, then the gaseous water has the same identity as the liquid water did. That's why B is the best answer. It all has to do with the chemical identity of the substance. Did not change in this process. All right. Oh, we got a table here. Let's see, 14. All right, let me see. We've got 1, 2, 3, 4, 5 across. Here we go. And in the first column, we've got a symbol. And the second one, we've got number of protons. And the next one, we have number of neutrons, and then number of electrons, and then net charge. Okay. So what are we given first? Well, we're given this one. Let's see, we've got 3 of them. So let's do 3. Go. The first one we're given is 2O6SN, which is 10. We're also given this one. Okay. Oops. Do better than that. And what else are we given? We're given 35 here, and 40, and 36, and we're given 29 neutrons here, and a 2+ charge there. All right. I think that's all we're given. 1, 2, 3, 4, 5, 6, 7. Yep. Let's use a different color. All right, we want to fill in the values for each one of these. First of all, do we have enough information here to put that there? The answer is no. We need a periodic table. So you go to your periodic table, look up 10, and you find that it has 50. The atomic number is 50, which means that's the number of protons. Okay. Oh, one other thing we can fill in right now. There's no charge on that thing. So that's 0. How many electrons do you have? If the charge is neutral, you have exactly the same number of electrons. How about neutrons? Subtract the protons from the mass number and you get the neutrons. So let's see, that's a 6 there, 5 there, and 1 there. 156. Okay, how about this one? Well, we want to put the symbol in here. 35. Look up 35 on your periodic table, and you find that it's bromine. But notice that the difference in protons and electrons is 1. You have 1 extra electron, which means a -1 charge. That means you need a -1 there. Now, you can, but you don't have to, put the mass number, which would be 75. How about this one? Well, iron, we have to look that one up. Iron is 26 protons. Okay. And if you have a 2+ charge, that means you got electrons, you have 2 less, or I should say fewer, 2 fewer electrons than you do protons. You have an excess of 2 positives. So that means the electrons has to be 24. That fills in the chart. All right. Now we're going to name some compounds. Let's see, 15 through 21. All right. CF4. You have to ask yourself, type 1, type 2, or type 3. Both of these are non-metals. So it's a type 3. That means all you have to do is name the element using the binary standard and say how many of each one there happen to be. Remember, if there's only one of the first one, you don't say mono. You just write the name. That's carbon. And this is fluoride. But how many of them are there? There are 4. You need to know your prefixes. The Greek prefix for 4 is tetra. Okay. Next, LiH. LiH. Okay. This is a type 1 compound because lithium is an alkali metal, only 1 possible charge. It's a +1 charge. That means this is the case where hydrogen is a -1 charge. When hydrogen is the second element combined with a metal, it's a minus charge rather than a plus charge. So this would be lithium hydride. All right. How about COI2? Type 1, type 2, type 3. It's either a 1 or a 2 because you have a metal and a non-metal. But cobalt can have a number of charges. Right? We have to say what the charge is. So we say cobalt, iodide. Iodine is always a -1 charge, so that's 2 minuses. This means 2+ here. There you go. 18. AgCl. All right. Type 1, type 2, type 3. Metal, non-metal. It's a 1 or a 2. Silver is one of those transition metals that only has 1 possible charge. Right? Silver, copper, and cadmium. I believe. Let me check myself on that. This will be in the periodic table. No, sorry. Silver, cadmium, and zinc. So silver is a +1, chlorine's a -1. All you have to do is say silver chloride. That's unambiguous, not redundant. Because silver can only have one possible charge. That makes it a type 1 compound. 19, HNO3. And we're told in aqueous solution. That means you have to name it as an acid. So HNO3, NO3 is nitrate, right? Got an oxygen, so you don't say hydro. H become X. This is nitric acid. N2O5. Non-metal, type 3 compound. We say di-nitrogen pentoxide. We leave the A off of penta just for aesthetics. And let's see, NH4. These are two polyatomic ions. Now, when we name, we have to treat this cation as if it were a fixed charge metal. It's not a metal, but it's a fixed charge. So we treat it like a type 1 compound, right? This is a +1, this is a -1. So all we have to say is, what is the name of that polyatomic ion? Ammonium. And what is the name of that polyatomic ion? Nitrate. There you go. Now we're going to go the other direction. We're going to take names and write the formulas. Let's see, we've got 22 through 27. Oops, we're still using purple. Go back to black. Right. Magnesium hydroxide. What type of compound is that? Magnesium is a fixed charge alkaline earth, +2 charge. So it's magnesium with a +2 charge, and then the polyatomic ion hydroxide is a -1 charge. Right? So remember, when you have polyatomics, if you need more than one of them, you have to use a parentheses, because it's a group of atoms that behaves as a single ion. You cannot change the subscripts. So you put a parentheses around it and make 2 of them. Now you have 2 negatives against that 2 positives. Now, properly, you don't have to write the charges. I just did that for bookkeeping purposes. There's the compound. Dibromine heptoxide. Bromine and oxygen, both nonmetals. This is a type 3 compound. So all we have to do is say how many bromines and how many oxygens. Right? Those are the easy ones. Manganese 4 oxide. So in this case, you have manganese with a 4+ charge and oxygen with a 2- charge. Right? So in that case, you need 2 of these to balance those 4 pluses. Okay. There's your compound. Sulfurous acid. Right? We know it's going to have hydrogen first. And working backwards, us's are derived from ites. Ite becomes us. So sulfite is the original polyatomic. Right? So what's the charge on that polyatomic? Sulfite is a 2-. That means, in this case, hydrogen is a +1. So we need 2 of those +1s. That balances the charge. So there's your, and actually, if we were to write it correctly, it would be an aqueous solution. Same for acetic acid. You have a hydrogen first, and then you have the acetate polyatomic ion, C2H3O2. I'm not going to count off if you leave this off like that, but properly speaking, we should have aqueous in there. Nitrous acid, HNO. Which one of the polyatomics? Us is derived from ite, so nitrite, NO2. There you go. All right. Okay, now we're up to 28. Let's see, we got a problem here we need to solve. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. A manometer. Okay, we've got a sample of gas here. And it's attached to manometer. Okay, so this is 2.34 liters, 2.34 liters of gas. The mercury level in the arm of the manometer attached to the gas sample over here is 24.3 torr lower than that of the arm open to the atmosphere. So this is going to be down here. This is going to be up here. And the difference is 24.3. 24.3 torr difference. Okay. Let's see. Atmospheric pressure is measured to be 1.23 atmospheres. I don't know how that could be. Usually not that big a difference, but this is a theoretical problem. Maybe we're on the shores of the Dead Sea. So atmospheric pressure here is equal to 1.23 atmospheres. All right, that's everything that we're given. What's the pressure of the sample in here? All right. First of all, is the pressure inside the cylinder greater than or less than atmospheric pressure? It has to be greater than to be pushing this down further against both this weight of mercury and that pressure of the atmosphere. So the pressure inside the cylinder has to be this one plus that one. All right, but we can't add, these are different units. So let's look at the answer. The answer is in torr, right? So we want to convert this to torr. What is a torr? 1 torr is 1 millimeter of mercury, right? So 1 atmosphere, use our dimensional analysis, is 760 torr. Okay. So let's see what that value is. $934.8. 934.8. We'll round it off as soon as we, well, no, if we've got to add them together, right, we can only have 3 figures here, so it's 935. All right, so then we can add 935 plus 24.3. 5, 9. Right, so we have to chop it off there. It's 959 torr. Which one is that? That's E. Okay. Sometimes it helps to draw pictures. If I didn't draw that picture, it might be difficult to tell whether I wanted to add this to the atmospheric or subtract it from the atmospheric. All right. Number 29. Let's see. Complete the following. Because real gas particles have attraction for one another, okay, real gas, attraction, okay, and which one of these statements is true? Real gases act most ideally at standard temperature and pressure. Is that true? Well, they do, but the statement implies that that's the only place they act ideally. Right? So A is possible, but not the best answer. We assume gas particles have negligible volume. Does that have anything to do with attraction? No. Has nothing to do with attraction whatsoever. 1 mole of an ideal gas at STP has a volume of 22.4 liters. That's true, but it has nothing to do with the attraction of particles to one another. How about D? Real gases act more ideally at higher temperatures and lower pressures. That's the one. High temperature, low pressure, and that's because real gas particles attract one another. So what does that have to do with attraction? Well, if the temperature is high, then there's enormous amount of energy for every impact. So if those particles are attracting one another, but they're coming at each other at such a high velocity, they bang into each other, then the attraction is negligible. It has little effect. And low pressure, the attraction has little effect because there's so few of them. They don't encounter them, their neighbors as often as they would under high pressure. So this is a direct consequence of that attraction of particles for one another. And of course, E can't be true because this is the only one that is true. All right, 30. Let's see. Oh, you remember these. Yeah. So 30, 31, 32, and 33. 30, 31, 32, and 33. Right. So we're dealing with a 1 liter bulb at standard temperature and pressure connected to another bulb that's evacuated. We have 1 liter with a valve, and the other cylinder, we don't know what its volume is, but it's a vacuum. There we go. So let's see. We want to find a true statement about delta H for this one, and Q for this one, and W for this one, and delta E for this one. All right, so remember delta E equals Q plus W, just as a reminder. So when we open that valve, are these values, or any of these values equal to 0? Are they greater than 0 or less than 0? Right? So let's focus on Q first. Right? If this is at standard temperature and pressure, but we have to assume that the whole system is at standard temperature and pressure and doesn't change during the process. If the temperature does not change, then there's no heat transfer in or out of the system. So this one has to be 0. If the expansion of the gas into the vacuum is not pushing against anything external, because this is the system and this is the surroundings, right? So it's not pushing against anything in the surroundings. Work is also 0. Right? So 0 plus 0 equals 0. So we found that this one's 0, that one's 0, that one's 0. How about this one? Well, if there's been no transfer of heat, then the heat potential enthalpy must also be 0. That's the only possibility. So all 4 of those are 0 under this scenario. $34. Let's see, we're going to have to work a problem here. Choose the correct equation for the standard enthalpy. Oh, standard enthalpy of formation for CO gas. All right. So we want the standard enthalpy of formation for CO. Remember, when we write this one, this CO gas, this is under standard conditions. It's the most stable compound under standard temperature and pressure. So we work our way backwards, right? When we are considering heats of formation, we start with the product and work our way backwards, and we start with 1 mole of that product. Then we go back and we take each of the elements in their most stable form. So carbon in its most stable form is graphite. And we add it together with oxygen in its most stable form, O2 gas. Okay? And then we say, all right, we can't touch that, but we can do this one. So 1 carbon, we need half of that one. And then what's the delta H? Delta H 0 is given to us, actually. It's a minus 110.5. Minus 110.5 kilojoules. Yeah. Okay. That's how you write the standard enthalpy of formation equation for any compound. Oh, so that would be C. All right. We'll have to get to the answers in a minute. This one ought to look familiar. This is one of those word problems that throws a lot of irrelevant information at you. Nitric acid. Okay, we do need to know that. Was first prepared 1,200 years ago by heating naturally occurring sodium nitrate and sulfuric acid to produce sodium bisulfate, collecting the vapors of HNO3 produced, right? All that you don't need. We want to calculate the delta H, standard delta H for this reaction as written. And we're given the balanced equation there based upon those other heats of formation. Now, the nice thing about this is we could go to Hess's law, but it's not necessary because we know the heats of formation are given. Right? Remember when we're trying to determine the enthalpy for a reaction, if we have the heats of formation for each of the compounds, then we can calculate the delta H from those values. Right? If we've got sodium nitrate, which is solid, and sulfuric acid, which is a liquid. And we get sodium bisulfate, sodium hydrogen sulfate, which is a solid. And then hydrogen nitrate is a gas. Okay, let's see if that's balanced. One sodium, one nitrate, two hydrogens, one here, and one sulfate there. That one is balanced. And notice that the coefficients are 1, 1, 1, and 1. And remember the formula for calculating the enthalpy for that equation is equal to the sum of the enthalpies for the delta H's of formation of the products. And this would be multiplied by the coefficients, right? But the coefficients are all 1, so that's nice. And then subtract the heats of formation for the reactants. Okay, so this one's simple, right? Go over here, sodium bisulfate, which is minus 1125.5, minus 1125.5 kilojoules. Okay, and then we're going to add HNO3 minus 135.1, minus 135.1 kilojoules. Right. Then we subtract the reactants, and sodium nitrate is minus 467.8 kilojoules, and H2SO4 is minus 814, minus 814, 0 kilojoules. There we go. Okay, so now all we have to do is grab our calculator. Let's do this one, and then do that one, and then we'll finish it off. All right, so 1125.5, change the sign. And then 135.1. This one is minus 1260.6 kilojoules. Minus, and this one is 467.8 and 814. This is minus 1281.8 kilojoules. Okay, so this one becomes a plus. And then we just add them together. Right, so this is 212 kilojoules, positive 212 kilojoules. Oh, excuse me. No, 21.2, sorry. I read my calculator correctly. 21.2 kilojoules. So this reaction is endothermic. They could, there would not be a risk of overheating and boiling and destroying your equipment and so forth when they tried to do this back in the Middle Ages. Because it's endothermic, it's going to get colder, actually. All right, so that was C. Okay. Let's go to the next one. Okay, 36. The force between two bodies having identical electric charges. So it could be a plus and a plus, or a minus and a minus. Those two charges would be what? It doesn't matter. It's always repulsion. The only time you get attraction is when the charges are opposite. So this is a force of repulsion. Doesn't depend on whether they're negative, positive. And actually C, it does not increase as the bodies move apart, decreases, right? Coulomb's law says the further apart they get, the less the force applied. And let's say E is directly proportional to the distance between them. No, it's actually directly proportional to, let's say we need a constant, and then we need the size of the charge. So let's see, charge of, let's see, C1 times C2, and then the distance between them is squared, right? So this is just a constant. This is the value of the charge in coulombs. This is the distance between them. It's the square of the distance to which they are proportional, inversely proportional to the square of the distance. All right, so the only correct answer in there is A. It's a force of repulsion. Okay. Which of the following molecules have no dipole moment? All right. 37. A, B, C, D. Yeah, and then E is none. Okay. Did I lose somebody? 1, 2, 3, 4, 5, 6. Yeah, I did lose somebody. Okay, we're looking for no dipole. So our choices are CO2, NH3, H2O, and all have no dipole. You know, that's a bad choice. Is it all have dipole or all have no dipole? Okay, because if it's all have no dipole, then none have a dipole. Or this must mean none satisfy the condition, which means they all have a dipole. All right, so in order to tell if they have a dipole, you need to know two things, correct? You need to know bond polarity. That's one. Two, you need to know geometry. Right? So we've done carbon dioxide before, and you can do the Lewis dot structure, and you'll end up with this situation here. That is non-polar. The bonds are polar, yeah. Right? But they're equal and opposite, so the whole thing is non-polar. Ammonia is like this. It's polar in that direction. Water is like this. It's polar in that direction. So A is the correct answer. It has no dipole. I'm losing everybody. Well, that's all right. Either you can't stay or you don't want to stay, which is not my problem. 38. Choose the molecule with the strongest bond. All right, remember this one? B, C, and D, or E, all equal. All right, we've got difluorine, dichlorine, dibromine, and diiodine. All right, these are in order from top to bottom of the halogens, and these are dihalogens. All right, which has the strongest bond? These are all covalent compounds. And what you're looking for is how do they overlap their orbitals? Right. Since they're identical molecules, there's no polarity in the bonds. They share equally. Right. So what you want is the maximum overlap of orbitals in order to get a strong bond. Right. So iodines, let's see, 1, 2, 3, 4, 5. This is period 5. This is period 4. This is period 3, and this is period 2. So you're going to get more overlap as you, right? These are period 5 orbitals are big. Get smaller, which means you can move the nuclei closer together and get more overlap of the orbitals. So the strength of the bond is increasing in that direction as you get more overlap of the orbitals. Okay? Here's the kicker. When you get to fluorine, the fluorine atoms are so close together that overlap cannot overcome the repulsive effects of the protons and the electrons. You got protons in the nucleus, electrons in the other orbitals that are repelling one another, right? So you actually increase strength here, and then you decrease strength from here to here, right? So up to here, you're increasing the strength of the bond, right? But when you go from here to here, you're decreasing because of that. Those nuclei are close together, and the core electrons plus the repelling one another, plus the protons in the nuclei are repelling one another, which weakens the bond. So this forms the strongest bond out of all of those, the dichlorine. All right, 39. In the gaseous phase, which of the following diatomic molecules would be the most polar? Right, since they're in the gaseous phase, now we don't have to deal with all that other stuff like liquids and solids. Right, they're independent molecules, so we can treat each one as a separate unit. Right, the most polar bond in that group is going to be the one where the metal and the non-metal are furthest apart in the periodic table. Right? Remember, the electronegativity increases lower left to upper right. Right? And they're all, well, let's see. You got fluorine is the most electronegative. Right? So cesium fluoride, C, D, we got an E, yeah, we got an E. So we got lithium fluoride, we've got sodium fluoride, we've got sodium chloride, and cesium fluoride. Cesium fluoride. Okay. Which ones of these pairs are the farthest apart from each other in the periodic table? If you just look at the periodic table, you'll find fluorine is in the upper right hand. Right? Chlorine is just below it. Cesium, lithium is in the top rank of the alkali metals. Sodium is below it. Right? So lithium and fluorine would probably be the least polar, or maybe sodium and chlorine. Actually, sodium and chlorine might be the least polar. It'd be a toss-up between these two. But sodium and fluorine would be a greater difference. Cesium and chlorine would be even farther apart because cesium is the lower left-hand corner. But cesium and fluorine are the farthest apart in the periodic table. They should have the greatest difference between their electronegativities, which would cause the bond to be the most polar. Right? So A would answer that question. Let's see. Least polar, if that question came up, what would be the least polar? The ones that are closest together. Probably, well, it'd be a toss-up between lithium and fluorine and sodium and chlorine being the least polar. Let's see. Sodium and chlorine would push the nuclei further apart, so there'd be less repulsion. I think, I'm just guessing, I think this one would be the least polar. The only way to know for sure is to look up their electronegativities in a periodic chart that's set up that way and do the difference. I don't think there's one given in the useful information. I don't believe I included that one. No. So there's really no way to tell without that information. All right, 40. Use the molecules below to answer the following question. Which of the molecules have equivalent carbon-carbon bonds throughout the molecule? They're all exactly equal. What do we mean by exactly equal? Equivalent. Equivalent how? In bond length and bond strength. Right? We have these three possibilities. And remember, in organic chemistry, when we draw a line, wherever the line connects, there's a carbon. That's where we've got a carbon, 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 carbon. And let's see, double bonds are here, here, and here. And this is C6H6 and C6H8 with double there and double there, and C6H10 with a double there. Okay. For these two, these bonds right here would be equivalent to one another. And these bonds would be equivalent to one another. But they're not the same throughout. And similar, that would have no equal here. Right? Okay, so by process of elimination, this one's probably the one that has the same bond length and same bond strength for each one. This is a conjugated system. And it's a special kind of conjugated system. Whenever you have single, double, even in a line, you, let's see, what's the right term? You spread the electron density out over, shoot, my mind's gone blank. Anyway, this one we often write like this to show that all of these bonds, this double single is actually not true. The spread here is over the entire molecule. That stabilizes it. This is an aromatic ring, benzene. And the I almost had the right word. Anyway, the answer is this one, A. This is number one, which in the answer would be A. This one has same bond length, same bond strength for the entire molecule. All right. What's the bond order for this species? Right? If we write this molecular orbital shorthand, and we have sigma 2s, we have sigma star 2s, then we have sigma 2p, and we have pi 2p, then we have pi star 2p. I think that's as high as it goes. We got 2 electrons here, we have 4 here, we got 2 there, 2 there, and 2 there. So what's the bond order? Well, we take the electrons that are in bonding orbitals, right? 2 plus 2 plus 4 minus 2 plus 2 and divide by 2. Right? So this 2 and this 2 cancel by those 2. We have 4 divided by 2, which is equal to 2. So the bond order for this particular diatomic species is D, 2. Okay, that was molecular orbitals. Now we're going to switch back to valence bond and say something about the hybridization of these particular carbons. Right, we have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. We got a double, single, single, single. Double, single, 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 and then a triple with a nitrogen. And let's see, we have 2 hydrogens here. Yeah, 2 hydrogens here. We have an oxygen here. We have a hydrogen here. And then we have 2 hydrogens there. Okay, so this is 1, 2, 3, 4, and 5 carbon. All right, what's the hybridization? Remember, all you need to know is how many groups are around the carbon in question. Right? Well, first of all, do we have octets? We have 1, 2, we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Right? And for kickers. All right, so everything's complete, right? How many groups are around this one? Well, if we draw these hydrogens in like that, that's 1, 2, 3, sp2. 1, 2, 3, sp2. 1, 2, 3, sp2. There are 4 electrons up there. 1, 2, 3, 4, sp3, and 1, 2, sp. So that would be A. A satisfies is the correct answer for that one. All right. And 43. Which of the following statements describes the Heisenberg uncertainty principle? All right. Let's just state what the Heisenberg uncertainty principle is and see which one of these best matches it. In any object, particularly those that are very small, you have two ways to characterize it. You can characterize it by its position, right? And that's the uncertainty of its position. Or you can characterize it by the uncertainty of its, its momentum, which is mass times velocity. That's what that is. And let's see, I paint myself into a corner. I never can remember it's greater than or less than. Okay. It's not here. Huh. In relationship to Planck's constant over, I think it's 2 pi. Maybe it's 4 pi. I think it's greater than or equal. So what we're saying is that when this uncertainty is really big, this one can be small. And for small objects, the mass is not going to change. So we're actually focused on the velocity. So if you don't care about where it is, you can make this one really small. The uncertainty in velocity. So you can know the velocity, but you can't know where it is. Or you can know where it is, but you don't know its velocity. All right, so let's see which one of those matches. A says it's impossible to accurately know both the exact location and momentum of a particle. That's it right there. That's the best statement of all of those. How about 44? What 44 is asking is, why did Mendeleev get credit, the most credit for the periodic table? And I've said it before, I'll say it again. Mendeleev used his periodic table to predict the existence of yet undiscovered elements. And not only that, he characterized them relative to the group in which they were located in terms of its relative mass, some physical properties and chemical properties as well. And when those elements were discovered, they matched very closely to his predictions. So that's why, number C, he emphasized the usefulness in predicting the existence and properties of unknown elements. That's why Mendeleev gets credit for the periodic table. All right. 45. Okay. Nitrogen has 5 valence electrons. So that element has 5 electrons. Which of the following electronic configurations represents nitrogen with a -1 charge? So a -1 charge would be 6 electrons, correct? Okay. Now, notice they've left out the principal quantum number 1. We only have to focus on the 5 valence electrons because we're not considering the first period, or the n equals 1. We want n equals 2. So 2s and 2p are the valence shells for nitrogen. We've got 1 subshell here, and we've got 3 here, right? So if it's 5, we have 1, 2, 3, 4, 5. But we're going to add another electron. It goes in right there. So which one of those matches? Looks like E is your best choice. All right, 45, 46. All right, we've got an element with the electronic configuration argon at its core. And I'm going to put in 18 here. Argon at its core. And then beyond that, we have 4s2. We have 3d10 and 4p2, I believe. Okay. Now, the question is this a non-metal transition element, metal, lanthanide, or metalloid? Right. So I would go look for the element. I'd find the element in the periodic table. And if we go down to the fourth period, and we go through the first two elements in the fourth period, which would be potassium and calcium, and then we go across the transition metals. Yeah. And then the first one over here would be gallium, would be 4p1, 4p2 would be germanium. Right? That's your element, germanium. Right? Now you can say something about what it is. Well, if you remember the division between metals and nonmetals, what you get is, let's see, here, you get gallium over here, and you get germanium right here next to that line. Okay? And remember what we said about these elements that are close to the line right in here. Sometimes they act like metals and sometimes they act like nonmetals. So they're called metalloids. See if I spelled that right. 2 L's. Metalloids. That's what germanium is. It's a metalloid, which is E. All right, 47. In which group do all the elements have the same number of valence electrons? In order for them to have the same number of valence electrons, they have to be in the same columns. Right? So if we look at each one of these in turn, all we need to do to eliminate it is to find one in there that doesn't fit. Right? Silver, cadmium, argon. Argon's a noble gas, it's not a metal. So A can't be. Can't have the same number of valence electrons. Sodium, calcium, barium. Calcium and barium are alkaline earths, but sodium is an alkali metal. Right? So that one doesn't work either. Phosphorus, sulfur, and chlorine. Chlorine is a halogen. Phosphorus and sulfur are chalcogens. No, sulfur is a chalcogen, phosphorus is a pnictogen. Right? So they're all three in 3 different groups. Right? That doesn't work either. How about phosphorus, arsenic, and selenium? Well, phosphorus and arsenic are pnictogens, but selenium is a chalcogen. Right? So that one doesn't work. That means none of them have the same number of valence electrons. (48) Let's see. Which of the following was not an elemental property usually predicted by Mendeleev for undiscovered elements? What did Mendeleev not know about in his day? Well, they did know atomic mass. He used that to predict. They did know densities. They knew boiling points easily. And oxide formula was very common, is the way they described most metals in terms of their oxides. Right? The one thing that he did not have access to at that time was electron configurations. That system had not developed yet. So electron configurations were not part of Mendeleev's repertoire, his descriptive terms. All right, 49. Which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? Okay, let's write this one out. C2H6, 2C2H6, which is ethane. And then 7O2 gas yields carbon dioxide and water. 6 waters. And 4 CO2. All right. Take a look at the answers. What we're looking for is stoichiometry here and limiting reactants, right? So we're focused on this side of the equation. And notice that what we're saying is sometimes we're saying equal masses of ethane and oxygen, so forth, equal numbers of moles, so forth and so on, more mass of one than the other. So I think it would be informative to do the stoichiometry in terms of equal masses. How many moles would be equal mass? Because we can't say anything about stoichiometry unless we know the number of moles. So if we start with equal masses, then that gives us a center point that we can move either way. All right, so what's the let's see, molar mass of C2H6. Let's do that one first. 2 carbons, 12.01, plus 6 hydrogens, 1.01, would be what? And plus, this would be 30.08. Yeah, grams per mole. All right. How about oxygen? Well, O2 is just 2 times 16, which is 32 grams per mole. Okay. So what will be the stoichiometry here is 2 moles of ethane to 7 moles of oxygen. What would be the mass stoichiometry? Well, the stoichiometric mass would be, this one would be times 2, right? 2 moles, 2 times this value would be equal to 60.16 grams. So 60.16 grams here, and 7 would be 224. 224 grams there. That would be a stoichiometric mixture. That many grams of ethane, that many grams of oxygen. Okay, now let's see what our possibilities are. A, if we have equal masses of C2H6 and O2, there is no limiting reactant. If you have equal masses, let's say we have 224 grams of O2 and 224 grams of ethane, then oxygen is limiting, right? Right, so that's false. Can't be. How about B? If we have an equal number of moles of C2H6 and O2, there's no limiting reactant. Well, equal number of moles would be, say, 2 moles here and 2 moles there. Then we don't have enough oxygen. It would be limiting. Or if we had 7 here and 7 here, then this would be all used up and that would have some left over. Oxygen will still be limited, right? So equal number of moles would give us a limiting reactant. So B can't be it either. How about C? If we have more mass of C2H6 than O2, then O2 must be limiting. If we have more mass of C2H6, yes. Instead of equal masses, if we have more mass of this one than that one, right? then this one is going to run out first. So C looks like it's the best answer. Let's look at D just to be sure, right? In case there's a mess up here. If we have more mass of oxygen, then C2H6 must be limiting. More mass of oxygen means that this one is still limiting. Let's see. If we have more mass of O2 than C2H6. Okay. We have to base C and D upon A. If we have equal masses, there's a certain condition. But if we have more mass of C2H6 for C, if we have equal masses, then if we have more mass of this one, then this one, if they're equal, 2, 2, 4, if they're equal, then they have one condition. But if there's more of this one, then definitely oxygen is limiting. Right, so C is definitely correct. Right, if we start from equal amounts and then say we have D, more mass of O2 than C2H6 must be. If we have more mass of O2, then we still don't have enough. All right, we'd have to have 4 times that for them to even be stoichiometric. Right, so the best answer is C, although D is not giving us enough information, but C is the best answer out of all of those. That's the only thing I can say about it that makes any sense. All right, 50. All right, what are we doing? Which one of these is paired incorrectly? All right, A, B, C, D, and E. All right, is H2SO4 a strong acid? In chemical terms, yes, it is. The first proton that comes off of H2SO4 is completely dissociated. Right? So when we put it in water, we get one of these plus one of these. Right? And it's all the way over to this side. That's a strong acid. Okay, so that's true. That first one is a strong acid. How about HNO3? Is it a weak acid? No. This is a strong acid also. Right? So that's the one that's false. We can look at the others. Barium hydroxide. Barium hydroxide is, barium is an alkaline earth. And all alkaline earth hydroxides are strong bases. They're not very soluble, but they're still strong. Strong acid, HCl, that's true. Weak base, NH3, that's also true. So this is our best answer. That one is not a weak acid, it's a strong acid. '51 coming up. Yeah. Okay, 51, 2, and 3 are based upon that first statement. 51, 52, and 53. All right. So let's see. Aqueous solutions of barium chloride and silver nitrate are mixed. Aqueous barium chloride. You got to be able to write the compound. BaCl2, aqueous. Right? Barium is 2+ charge because it's an alkaline earth. Chlorine is a halogen with a -1, so we need 2 of them. And we add to that what? Silver nitrate. +1 charge, -1 charge. And that is completely soluble. Right? What is it going to make? Well, it tells you there, but we really don't need that. I mean, I can write what it's going to give us right up here. Silver chloride, solid, plus barium nitrate, aqueous solution. Right. Okay. So the first one, 51, the balanced molecular equation contained which of the following terms? So we need to balance this correctly. Right, we have barium, one barium here, one barium there. Okay, we're good. Two chlorines, we need two chlorines here. Right, that gives us two silvers, two nitrates, two nitrates. That's balanced. Now you can use the budget method if you want, that's fine. But these double replacement reactions typically are very easy to balance without the budget. So there is the molecular equation. Okay, so which terms are there? 51. AgCl, and notice that we're using coefficients in here also, right? So we need a 2 there. So A is not the correct answer. B is the correct answer. 2 AgCl solid. 2 barium nitrates? No. 1 barium nitrate aqueous? No, because that nitrate it's only one of them. It's not written correctly. And they're not 3 silver chlorides. So B is the correct one here. B. Let's see. 2 silver chloride solid. That term is in that equation. Okay. The complete ionic equation, remember how to write that? This is an aqueous solution. That means this one is aqueous plus 2 chlorides, aqueous, plus 2 silvers, plus 2 nitrates. And these are aqueous and aqueous. This one doesn't change. 2 silver chloride solid, plus a barium, 2 plus aqueous, and 2 nitrates. That's the complete ionic equation. Now, which one of these are in there? Let's see, 2Ba2 plus. Now, there's only one of them. Can't be that one. 1 chloride. Now, we need 2 of them. C, 2 silvers. No, silver's tied up in this solid. Nitrates. Wait a minute, 2 silvers? Oh, here it is. Sorry, 2 silvers. Yeah, that one's good. 1 nitrate. No, there are 2 nitrates. Silver chloride, aqueous. Sorry, doesn't work that way. It's a solid. So that one, C, is 2 silver aqueous. That's a term that's in the complete. Now the net ionic equation, we take this one's on the reactant side, on the product side, cancels. This one is on, no, not on both sides, not on both sides. This one's on both sides. Well, that one cancels. So the net ionic equation, this is complete ionic equation. The net ionic equation is 2Cl minus aqueous plus 2 silver aqueous yields 2 silver chloride solid. Now notice these all have 2 coefficient in common, 2, 2, and 2. We can further reduce this. The net equation should be the simplest whole number ratio of reactants and products. So that means we would multiply by 1/2. That would cancel that 2, that 2, and that 2. Now the net is actually this one. There we go. So which one of these is there? Ag plus, but A, right? There's no barium, there's no nitrate, there's no hydrogen, and silver chloride aqueous doesn't exist, right? So this one is A. Okay. That answers those three. We're getting close. 54. Gas problem. Okay, you're holding two balloons, an orange balloon and a blue balloon. Orange and blue. All right. The orange balloon is filled with neon gas. And the blue balloon is filled with argon. Okay. The orange balloon has twice the volume of the blue balloon. All right, so we got to change that. This one needs to be twice as big as that. Okay. So let's see. The volume of argon and the volume of neon, what's their relationship? Well, this one is twice the size of that one, so that's 2 times that. Okay. The orange balloon has twice the volume. Which of the following best represents the mass ratio of neon to argon? So we're looking for mass neon ratio to mass argon. Hey.
We did it on Thursday, so I went ahead and log off on Zoom and
Okay.
I'm trying to put stuff.
Oh, all right, sure.
Are these the tests?
Yeah, that's the review document. Okay, so we're looking for the mass ratio. All right, what we can say something about the mole ratio first. So if this volume is twice that volume, the moles of neon are equal to twice the moles of argon. Okay. Now, to get from mass to moles, we need to know the molar mass of each gas. That's the only way we can get there. So what's the molar mass of argon? Well, it's roughly 40. And neon is roughly 20 grams per mole. So if neon has twice as many moles at 20 as argon does at 40, then we have equal masses of each one. Everybody see that? Right? This has twice as many atoms as that one. And each of the atoms is half the mass of this one. So if we go, we're going twice the mass this way, but twice the particles that way, and they even out. So the mass of each one relative to the other is 1 to 1. It's exactly the same mass in each one. All right, looks like we've got a calorimetry problem coming up here. $55. Okay. 45.9 gram sample of a metal is heated to 95 degrees and then placed in a calorimeter containing 120 grams of water at 21.6 degrees. The final temperature of the water is 24.5. What's the metal used? So remember, in a calorimeter, the calorimeter is an isolated system, which means that everything that happens in that calorimeter must, in terms of heat, must equal 0. So we start from 0 and we have a heat change for the water And we also have a heat change for the metal. Okay. Now notice we've excluded the term for a calorimeter. Right? We're assuming that the calorimeter is totally efficient and it doesn't absorb or give up heat at all. Right? This is a theoretical monster. So how do we calculate these two? Well, the Q for water is the specific heat of water times the mass of water times the change of temperature that it undergoes. Right? That's the water term. The metal term is the specific heat of the metal times, let's see, like that. Don't get them confused with the mass of the metal. This is water. Times its change in temperature. All right. So the specific heat of water is given to us as 4.18. 4.18 joules per gram degree C. The mass of the water is 120 grams. Right? So grams cancel here. How about temperature change? Final minus initial. So what's the final temperature of the water? Final minus initial. So the final temperature of the water is 24.5 degrees. Minus the initial, which was 21.6 degrees. Okay. Now, what happens to the metal? Well, this is the unknown. We don't know what it is. We don't know the specific heat for this metal. So that's our unknown. We do know the mass of the metal, 45.9 grams. What's the temperature change? Well, the final change, the temperature for the metal is the same as it is for the water, 24.5 degrees. But the initial temperature for the metal is 95.2 degrees. There we go. That's the problem set up. Now we just have to solve for that unknown right there. All right, so let's do this calculation first. Let's see. I'm going to subtract these two. It's easier for me to do it that way. 21.6 minus, okay. This is 2.9 degrees times 120 times 4.18. So this is 145, 4.6. Grams cancel. This is joules. Okay. Now this term right here is going to be 24.5 minus 95.2. This is minus 70.7 times 45.9. And this term is going to be, let me erase that because it'll look like it's part of this term. This is minus 3245.1 times the specific heat of the metal. Okay. All right. So now what do we do? Well, we can leave this one over here and put this one over here and make them both negative. Or we can move this one to this side, make it positive, and leave that one where it is positive. That's what I want to do. So this one comes to the other side as a positive, 3245.1 times the specific heat of the metal, and 1454.6 here. So now, oops, be consistent. M equals 1454.6 divided by 3245.1. Let's see here. And I get wrong answer. Hold on a second. 1454.6 and 32. Sorry. 5.1. That's better. So let's see. We got 3 significant figures. Yeah, it's kind of, I haven't kept my significant figures correct. So let me just maybe say it's 3. 0.448. And this is joules per gram degree C. So which one is that? Closest one to that one looks like it's iron. This is iron. Or B. So ask yourself, if I create a problem and give you different numbers, maybe it's not going to give you iron. Just remember how to work the problem. 56. All right, shifting gears again. Light. Let's see. For which of the following transitions, in other words, an electron transitioning from one quantum level to another quantum level, emits the longest wavelength. So which one of these transitions would give you the longest wavelength? All right, I like pictures, right? There's the nucleus. And then we have 1, we have 2, 3, 4 is even closer. Okay. So if an electron transitions from a higher to a lower one, which it looks like each one of those does, if it goes from 4 to 1, that's a big jump. If it goes from 3 to 2, that's a smaller jump. If it goes from 2 to 1, that's a little bit bigger jump than that one, but not quite as big as the other one. And if it goes from 4 to 3, that's a tiny jump. And if it goes from 4 to 2, that's a bigger jump. So the longest wavelength is the lowest energy. And the lowest energy corresponds to a short transition. The shortest transition here is this one, 4 to 3. 4 to 3 would be D. Okay. All right, 56. Let's see, 57. Okay. 57. Which of the following is an incorrect designation for an atomic orbital? All right. A, B, C, D, and E. All right, so our choices are 1s, 6s, 3d, 1p, and 4f. Okay. All right, remember, if we have n equals 1, or 6, or 3, or 1, or 4, what are the possibilities for L? In this one, the only possibility for L is 0. That's S. For 6, possibilities are 0, 1, 2, 3, 4, and 5. So it's S, P, D, F, G, and H. All right, so that's true. Right, so you can have an S for 6, and you can have an S for 1. That's good. That's good. We're looking for the one that's not right. How about 3D? Well, let's see. We have a 0, 1, and a 2. S, P, D. Okay, we're good there. All right. 1 can only have 0. S. That's the bad one. Can't have a P with n equal 1. And 4F obviously is 0, 1, 2, 3, S, P, D, F. So that one's good. So for 57D is the incorrect designation for an atomic orbital. All right, 58. Let's see. Molecule xenon difluoride. And what are we going to do with it? How many electrons surround the xenon, and what is the molecular geometry? All right. So we have to, our valence bond theory, valence electrons. Xenon has 8 because it's a noble gas. And fluorine is a halogen, so it has 7 times 2. Right. So that's 14 is 22 electrons, correct? Okay. So we have xenon. We set the fluorines there. So that's 2, 4. That's 4 is 18 electrons. Okay. Now we put, working from the outside in, we put 6 around each one of these fluorines. That gives it that an octet, and that's an octet. That's 2, 4, 6, 8, 10, 12. That's 6 electrons left over. They have to go on the center. So 1, 2, 3, 4, 5, 6. Okay, so our xenon is going to exceed the octet. Fluorines are good. Xenon exceeds. Right? What's the electronic geometry around that xenon? Well, first of all, how many electrons do you have? 6. Right. So, well, it's probably E. Because that's the only one with 6. But if we want to look at the geometry, right, 5 groups around xenon means trigonal bipyramid. So we have a trigonal in the middle, we have a xenon here, and then something there and something there. Right? The lone pairs go on the triangle, and the fluorines go at the apex. So that gives us a linear model. So E is the best answer. It has 6 electrons around the xenon with a linear molecular geometry. '59, I think. Yep. Okay, I got this one worked out down below. So let's see. Consider the following data. Use Hess's law to find the change in enthalpy for the following equation. Okay. This is going to take a little time, but we have time. 59. Right. So our target equation is calcium carbide. Calcium carbide. And 2 water yields calcium hydroxide, aqueous, and C2H2 gas. If anybody has probably maybe a grandfather that used to work in the mines, they used what they call carbide lamps. Calcium carbide and put in their lamp in the little container, add water to it, and it would produce calcium hydroxide and acetylene gas. So then they just light it, and that it would produce acetylene continuously for however long. And that's how they saw their way around in the mines. Right? You know, until one of them hit a pocket of gas and it blew up. Right. So they decided maybe open flames are not a good idea in a coal mine. Anyway, what we want to do is find the enthalpy based upon these 1, 2, 3, 4, 5 equations. All right. So I just start at the top. Calcium carbide. We have a calcium carbide there. Yes. The first one is calcium carbide. but it's in the wrong direction. Now it has the right number of moles. CaS2 solid, it has the right number of moles, but it's backwards. So let's switch that equation and change the enthalpy sign. Right? So this calcium carbide, solid, then be like this, and then we'd have calcium solid and graphite. How many graphites? Two graphites. And the value for that one is plus 62.8. Plus 62.8 kilojoule, I think. Yeah, kilojoule. Okay. So these are going to be the delta H's for each one. All right, so we've used the first one and we've taken care of that from the equation. Now, what's the next one? That's not one we need yet. Calcium hydroxide, the third one, is written in the correct order and with the correct number of moles. So we have calcium oxide, solid, plus 1 water. So let me move this back up here. Calcium oxide solid plus 1 water yields calcium hydroxide, aqueous. Okay, so that third equation gives us this one with minus 653.1 kilojoule.
635.
635?
Oh, I'm sorry. No, you're right.
Yeah. Yeah, you got to keep up with me. I mean, check me on that, because
Sorry.
I think I have written it backwards before, because I was doing the same thing you were doing. I was looking at the wrong line. Okay, so now we've taken care of this one with that equation. Okay, and one of the waters, but we need acetylene up there also. So acetylene is on the wrong side of the equation, but it's the right number of moles. So we need to flip that equation. All right, we need to put 2 CO2s on this side. 2 CO2 gas and 1 water yields acetylene, C2H2 gas plus 5 halves oxygen. And now we need the enthalpy is going to be reverse the sign because we flipped the equation. So this is plus 1300. That should have a period there. Kilojoules. Okay, so we've taken care of the acetylene. All right. And the waters, actually. So we got the waters done with these two. Okay, so now we're going to need that one. And we've used this one and this one, that one, and this one. So the ones that are standing out that we've got to get rid of that aren't in the target equation are these species right here. And here. All right. So let's go back and look at the ones we haven't used yet. All right, we skipped over the second one. That's calcium and calcium oxide. Calcium and calcium oxide. So calcium needs to be on the right, calcium oxide on the left. That's written correctly. No, it's backwards. Excuse me, it is backwards. Right. Calcium oxide, it needs to be flipped. All right, so that gives us 1 calcium. Oh no, hold everything. We're trying to cancel these things. trying to cancel that one. So calcium oxide does need to be on the right. All right, so we'll write it as is. Calcium plus a half oxygen yields calcium oxide, solid. Calcium oxide, solid. Yep. Okay. So now that we can incorporate minus 635.5. Minus 635.5 kilojoules. Okay, that takes care of this one here. Takes care of this one right here. Okay. So now we want, let's see. Which one did we skip? 62, 635, 1300. The last one, right? The last one, graphite. We need to put graphite over on this side. And it's already there. But we need two of them. Right? So we need 2 carbon graphite, taking the last equation, and 2 oxygens, right, yields 2 carbon dioxide. Okay. Now, we don't have to change the sign, but we do have to double it. So minus 393.51. Let me do it this way. Minus 393.51 times 2 equals. Here we go. Minus 787.2. There we go. Now let's see if we did cancel what we wanted to. 2 CO2s here, here, here. 2 graphites. Yep, there. And we've got 5 O2s over here, which is what? 5 divided by 2 is 2.5, isn't it? Right. So here's the 2, and here's the half. Takes care of that one. Okay, we have anything left over? That one, those cancel. That one, cancel. Okay, we're good. So now we just add up our terms. 62.8. Subtract 653.1. Add 1300. Subtract 635.5. And subtract 787.02. So I get minus 712.8 kilojoules. All right. Let's scroll down. This is one, this doesn't have a, it's not multiple choice. 70, let's see. Here it is, 712.8 or 82. That's good. I'll accept that. Actually, since this one only goes to the decimal point, it probably should be 712. Minus 712, be correct. All right. That took some time. 59. I think there's just one more, isn't it? 60. Is that right? Yep, just this last one. Okay, we're going to use little valence bond theory again. All right, so we have, we need 4 places here. Yeah. This is molecule A, B, and C. And we need here for electronic structure or geometry. And then we have hybridization. And then we have bond angles. Bond angles. Okay. We're given this one right here, SE3. And then the rest is from the description. So molecule A has hybridization of sp3, yes, on the central atom. Molecule B has 2 more effective pairs around the central atom. So if it has 2 more pairs, we have to bring in Ds. Right, so we need 2 Ds with sp3. Molecule C is diatomic and consists of 1 sigma and 2 pi's. The only way that you can get it's diatomic. If it's got 1 sigma, then the only place you can put the pi's are in that bond. So if this is sigma, you have to put both pi's there. That's the only way to do it. The hybridization there has to be around either one, has to be sp, right, for a linear geometry. This one has 6, so it's octahedral. This one has 4, so it's tetrahedral. Okay. Now the bond angle for tetrahedral, you just have to memorize it. 109.5 degrees. Octahedral, right? If you draw the octahedron right here with your something in the middle, then you have the possibility of only 2. All right, between this and this one is 90 degrees. Between this one, and this one, anything down here is 90 degrees. And between this one and this one is 180 degrees. So you can have 90 or 180 possible bond angles. And for linear, there's only one possibility. 180 degrees. Now I didn't bother with examples, right? If examples show up, right, a good example here would be maybe carbon tetrafluoride or methane, be a good one. Octahedral, sulfur hexafluoride would be a good one, right? And for this one, linear would be, say, dinitrogen or carbon monoxide would be a good one. Possibilities. All right, that's it. That's all the reviewing.
And the test is gonna be on next course, like regular class time.
Yeah, I looked for an exam schedule from the college, but I couldn't find one. So maybe they've given up on that. All right, so we'll just have the exam on next Tuesday. I'll be here Thursday, and I'll Zoom in case anybody has questions. You've been studying and you got questions, and come to me during that class period, 12:30 to 1:45, and I'll be here. I might be sitting off camera, but if you speak up, I'll hear you and come answer any questions you have about this. But that's all the review I'm going to do. What you can do is go back to any one of the review documents in the past. If you're weak on something, I'd practice that. I wouldn't try to practice strengths. I mean, they make you feel good, but they don't help you any more on the test. Right? So practice the stuff that's difficult and get better with that.
Are they all gonna be like mixed, like chapter 1, then chapter 9, or like they're all gonna be mixed? Or are they gonna
Yeah, they'll be mixed up. Yeah, they'll be mixed.
The switch is gonna be hard.
Yeah. In fact, I noticed when I was reviewing that some of the explanations came easier this time than when the first time I went through, because now you have background from later chapters and help you understand previous chapters. It makes it easier for me to explain them. Because before I didn't want to introduce a topic that we hadn't covered yet to explain something, but now you have access to all that information. Okay. Any questions from the Zoomers? Yay, we're gonna stop the share. Oh, let's see, somebody chatted. Oh, sorry about that. Yeah, this test is going to be on Tuesday. It'll be available on Brightspace if you need it. But if you take it on Brightspace, if you're not coming in now for the rest of the semester, you've got to deliver your. So I just did Tina's. So everybody else has to get their lab notebooks to me. Let's say by the final exam. I'll give you enough time to do that. So by the final.
I was planning on coming in for the final exam. I have stuff to upload, but if it doesn't upload, I'll bring it in either Thursday or by Tuesday.
Yeah, either day I'll be here.
Okay.
Yep. Okay, and if you have any missing assignments, or if you look at your grade book in Brightspace and you see zeros here and there, that means I don't have that assignment from you. And if you're missing that assignment and you want that grade to be not a 0, then you need to turn something into me with enough time for me to grade it. Things are kind of getting or telescoping here at the end. So I'm gonna grade things first come, first served. And if I run out of time, then even if you submit it late, it might not get graded.